So this is my project about the Harris corner detector. So basically it's a computer vision algorithm to detect corners using linear algebra. So basically, here's the general process. So you color to grayscale. You say take a digital image, and then you do a spatial derivative calculation, and then the structure tensor setup, and then you actually do the Harris response calculation, and you do a non-maximum suppression. So pretty much it's basically you take the value of the grayscale pixels with respect of the weight of r, which is the Harris value, and then you take the derivative with respect to x and I of x, the identity of I and the identity of y, and then you do the tensor setup and create the tensor m. Then you do the Harris response calculation, which is just lambda minimum is roughly equivalent to lambda 1, lambda 2 of lambda 1 plus lambda 2 times the determinant times the tenor sensor. And then you find the trace. Sorry, this was trace, not tenor. I just mixed that up. And then you just use the Harris calculation, and that's pretty much it. So this is the Matlab code behind that. So again, we're just importing an image file. We're just going to show it, show the original. We convert to grayscale to make it a lot easier. And then we apply the Sorbel operators, which are just two matrices. And as you can see, the column 2 is all zeros and column 1 is all zero. And these are just transposed, so they're just rotated essentially. And so that allows you to do the x and y convolution of the matrices a lot easier. So here's again that xi, so it's the identity matrix essentially. And then you take the image for each pixel of the image, and imagine it's a 3x3 box. And so that would be basically imagine this as the box, these matrices for both x and y. And then you just take that with respect to ix, iy, and ix of xy. So you're just squaring these two and multiplying them by each other. And then we have to define the kernel size, which is going to be 3 due to size of these matrices. Then we find the sum of the products of the derivatives of each pixel using the kernel size, so it's just sum all. So we're just adding them all together. And then you take the convolution again, redefining the matrice size, and then k is just an empirically defined constant that we use, and then a threshold for identifying the corners, because if it's too high, it's going to not do it. So then we actually do the calculation of r. So our average is just 0, so we're just stating that. And then for each x equals 1, so the number of rows, number of columns of each pixel. So we find m, which is, this calculation right here, which is the structure tensor, which is the sum of these values of the matrice. And then to calculate the response to the detector, it's just the determinant of m minus k times the trace of m squared. And then we just have a threshold of r, so basically, how sensitive is it? Then we just, im is just the equivalent for the image, so we just insert markers for the first threshold. Then we take the sum of r, which is just r average plus r, and then we define the average, which is r of time, divided by the number of rows and columns of the image itself. And then we get a calculated ranges of r, which is basically just how many r values are in the objects. So again, we just show the image of the original, and then read to green. So you'll see the first r value, and then the range is in the red. So let's actually run this. So there's the original image of the building. And then here's the second. So this is with a quite high r value. And then here's the range of the limited r value. And so as you can see, it works actually pretty well for detecting corners. And it's very, very good along these lines you can see here, and you could extrapolate data from that, which would be pretty interesting. And the clouds are cool because, here you can see that there are some data points, like on this cloud, for example, and on this cloud, but they aren't included here. So that's just an application of linear algebra. If you are interested in the code, it's down below.